Okay, so let's move on. In this chapter, we are looking at hardening rules, and um, this would be more towards the option available in the material properties. Apart from the first two things, the important thing that we'll learn here is isotropic and kinematic hardening. So before I move into this chapter, I would like to recollect or re-highlight on this thing. While we discussed the nonlinear theory, let me go to the right page here. It is page 28. Yeah, page 28, page 28. Yes, here it is. So in the theory part of this training manual, we have this module on hardening rules. That's where we discussed this initially, and we talked something called as Boschinger effect. There will be something called as isotropic hardening, and as well as something called as kinematic hardening, and that is what we are seeing here. Typically, if we are talking about isotropic hardening, this rule is basically ignoring the Boschinger effect and assumes that the current value of yield point does not change as the loading mode changes. So basically, when the loading is going from tension to compression, the yield strength is almost the same, and there is no Boschinger effect basically. And this is represented by a value of Rk, which comes in the material property. I'll show you where it is, of 0. On the other hand, when we speak about kinematic hardening, we are actually talking of again the Boschinger effect, but we are actually considering it and actually overestimating or over considering it. So as a consequence, obviously the material strain hardens anisotropically, and the yield strength is almost half of the yield strength in the tensile direction. And of course, this is all uniaxial test, and this represents a value of 1. However, for all practical purposes, or most of the materials behave or show a behavior which is somewhere between these two, that is 0 and 1. Okay, this is what it is all about. Let's move on to this chapter, which I forgot the page number, but let me try this. It's somewhere around there. Let me go to the right place. Yes. So we have a simple connecting rod kind of component which is subjected to a load in a particular direction. Thereon, this load is changed to the other direction, and we are going to simulate this particular setup. Okay. So first, let me obviously one of the two setups are there over here. One of the setup is more on isotropic kinematic hardening. In terms of material, this is a place where we give the value. It is 0 over here. So we are talking about isotropic kinematic hardening, and the material model is plasticity von Mises. We continue with that. Okay. We are holding the connecting rod at one end firmly, and on the other end, we are applying a particular force which can be seen as the tensile force at a certain location. And if you see the way it is applied, let me directly show you the graph. The way it is applied, if you observe here, so it goes from 0 to a certain value at time instant 1. Thereon it drops down to 0 again, and it remains at 0 after that. So this is like going in the negative direction, probably positive direction of x, comes back and it just stops over there. On the other hand, we have one more force which starts acting only at 2 units. Okay, so if you see here, it is from 0 to 2 seconds, it is almost flat or 0. Thereon it starts acting, it goes to a peak again, and again it drops down. Okay, we are talking about a load of in the tune of 11,000 Newton, and the other one is as well 11,000 Newton. So that should convey you. In one side, we are pulling it in the positive x direction with 11,000 newtons and releasing it back, and after it is released completely, we start applying the second load, which again goes until 11,000 newtons, and it comes back. So in Crux, this is actually a analysis for 4 seconds or 4 units of time, and appropriately the other parameters are changing. We need to ensure that the large displacement formulation is selected. Under advanced options, we are selecting force control method, and I think all other options remains the same. Okay. So here it is. Here is the setup. Typically, when we solve, let's see the results. There are different things that I might want to see, but first one is at 4 seconds. What is the displacement? It is in the tune of 5.469. Obviously, this would not make much sense till we start comparing, but at least one particular graph. What's happening to this? Okay, let me plot this graph. Yeah, this graph can make sense in itself if you observe this. So from 0 to a time instant of 2, somewhere here you can see we have actually covered an entire cycle. We are almost reaching 0 load over there, and thereon we start pushing it in the negative direction. But obviously you will see, because of plastic deformations, probably it has a displacement of 12 millimeters which remains over there, and thereon we start applying the negative force, and it takes some time, somewhere around 3 seconds, to actually go back to a neutral condition or below 0. Of course, it is not completely going below 0, and thereon we again the load is multiplied. So I would say the part is equally strong in both the directions, and that's why we see this particular behavior. Okay. Finally, again the reverse thing happens. It comes back to a 0 value, and because of permanent deformations induced in this part because of the 12 millimeter thing, we are ending up, after the entire cycle of compression and tension, we are ending up with a deflection of around 5 millimeters which remains in this body. Now if I take the kinematic analysis part of it, you can see here let me check the material properties first. So here we are using a value of 1. I'm not sure what happened to this, but this would be 1. Okay, this would be 1. Thereon, is it saved? Yeah, it is saved. Default 4. Thereon we are using a other way around. All other options remain the same. End time is 4. Advanced options, all other things remains the same. Okay. So only difference that we induced was through the material property, and we gave a value of 1. Let me just check the graph. Yeah, it's almost similar. Let me solve it now with a kinematic hardening value of 1. Okay. So while this is solving, we'll scroll through the training manual and see if there are any other concepts which I need to cover. So this is what isotropic hardening. We give the material 0 over here. In terms of nonlinear material curve, we are again using, there is some failure down here, that's okay. In terms of hardening factors, we are again using a value of, what do you say, we are again using a value of, I'm sorry, I was just talking about stress strain curve. I saw that error and I was lost in that. Okay, I'm talking about actually the stress strain curve, and in this case as well we are using bilinear material properties. We are talking about tangent modulus here again, and the image is a bit incorrect. We are actually using the tangent modulus, which is given here, 1/10 of the 1/10 of the property of Young's modulus. Okay, RK remains 0. That is what we discussed. We have applied the force. We do go ahead with that. Time curve, and what else? 11,000. This is what we saw. We apply it in the opposite direction. Take this, solve it. Yeah, all these were discussed. So at time instant 4, we saw a deflection of around 5.4 millimeters. We can also graph. This is a graph that we saw. Okay, and discussion. Yeah, that's what I discussed, wherein we are talking about at time instant 1, the displacement, or rather at time instant 1, the force is at its peak of the tension, and the deflection is maximum. At time instant 2, when the load is 0, the displacement is not 0, but it is actually 12 millimeters, and as we increase the load in the opposite direction, thereon it starts moving to 0, and until it reaches 3 when full reverse load is applied. At this instance, the UX displacement reaches a value of 1.5. Okay, and typically after that we reverse the load and it is slowly getting released. It again comes back or induces its permanent deformation and shows us a value of around 5.6 millimeters. Okay, now when we go in the other direction, we are talking about changing the hardening factor to 1. We run the analysis, so nothing much difference over there. On running, we will be seeing a graph which looks something like this. So in this case, at around 2 millimeters, because the hardening is huge, it has shown its effect down here. We are actually seeing a value which is somewhere near 0, and thereon it goes on the negative direction and it comes back. Okay, now if we see a bit more text on this topic, it goes on in this way, wherein so in terms of discussion, you will see being the yield strength being reduced in the case of kinematic hardening. The deflections that we are seeing are comparatively higher even on the compression side. So obviously on the compression side, the material is a bit more softer than what we saw in the isotropic kinematic hardening. As well, because of the softness, it will deflect enough in the negative direction, and when we release the load, we are actually seeing a permanent deformation on the negative side in the tune of -5 compared to what we saw on the positive side for the isotropic hardening. So that is what this text says. Frankly, it is a bit I would say confusing. You might want to understand this topic in a bit more detail by reading these two things a multiple number of times rather, and that should help you conclude. Okay, let me check the results down here for the nonlinear isotropic analysis. I faced a particular solution error when I solved the setup as it is. The only change that I have done in here is increase the convergence tolerance. Okay, convergence tolerance from 0.001 to 0.01. My observation in this setup, when I use a kinematic hardening of 1, it is experiencing what it calls as buckling kind of behavior, or it says the deflections are basically it is not able to attain a convergence at the appropriate time step, and that leads to changes in the that leads to the change which needs to be incorporated appropriately. Now obviously reducing the tolerance is not a good thing, but if we know why we are reducing it, it's fine. If you observe the results after reducing the tolerance are same as what you see in this particular PDF, so it's okay to do that. And this you can see it is showing the same graph as that what you saw in the training manual. Okay, so probably somewhere here, no, it was giving the error somewhere here. So when it is going in the positive direction, typically when the curve changes the direction, the software feels something is wrong and it might stop the convergence iterations and pop up an error. That's what was happening. So this is what it is all about, kinematic hardening and isotropic hardening. In the next chapter we'll move on to a bit more text down here. By the way, in terms of the software, it will use a value of 0.85 by default. If you want, you can play somewhere between 0 to 1. If you know for those particular material whatever is the kinematic hardening, you can use it appropriately. Obviously this is relevant in cases wherein the loads are moving from a negative to the positive direction, that is at the same location the part is experiencing compression and tension. Okay, so I believe these questions you should be comfortably able to handle and answer. In the next chapter we'll look into analysis of elastomers. Okay, that's it for this session. Thanks.